Okay, before you view this video, you'll want to print out the example template and notes that go along with it and read that through, because there's a lot of extra information that's worth looking at, and you might want to skim the section in the book to get ready for this. So we're going to take a look at estimating population proportions using samples. All right, and if we go to example 1 here, we have a mayor wanted to ban smoking in any park within city limits. Her assistant conducted a study of residents and found that 118 out of 185 people surveyed favored the smoking ban. So we're asked, what is the point estimate for the unknown true proportion of residents in this city who favor the ban? So remember, a point estimate, if we're talking about proportions here, the idea is we're going to use our sample proportion to estimate the population proportion. So point estimates are probably your best friend, because all we have to do is put down the proportion of the people favoring the ban in the sample, and that's it, we're done. If you want to convert that into a decimal or percent, go ahead, but a fraction is just fine too. So point estimate ones are the nicest ones as far as being easy. The problem is the book and the example and note template tell you, is knowing that p hat's 118 out of 185, that doesn't really give us any idea of how close that likely is to the real population proportion. So when we want to talk about how close our point estimate is, or how close our statistic is to the parameter, we can do that by figuring out a margin of error. So we have an older example here from the Barack Obama-Mitt Romney election, where they might report on the news, based on a new survey, Obama leads Romney 48% to 41%. But oftentimes they specify a margin of error. So here they say the margin of error of 3%. So in this case, telling us the margin of error is 3% tells us that the sample proportion is within 3% of the population proportion. And really, I should sneak the word likely in there, because we can't be guaranteed that, but we basically expect our sample proportion to be within 3% of the population portion based on this result. I'll show you how to calculate that later, but what we want to do here is make sure we understand what that would mean. So 3% margin of error, if we look at Barack Obama had 48% based on their survey. So if we go 3% down and 3% up, then we're going down to 45%, and we're going up to 51%. So what we're really saying here is, based on our study, we think that the level of support for Barack Obama is between 45% and 51%, because we've applied now the margin of error going in each direction from our sample proportion. In the most basic sense, we've just created what's called a confidence interval. So when you take your point estimate from a sample and then figure out the margin of error, if you go one margin of error below the proportion, the sample proportion, and one margin of error above it, you've created what's called a confidence interval. So we could say, in this case, we can be confident that the level of support for Barack Obama is between 45% and 51%. So we're going to get into the formulas a little bit more and figure out how we would do this all from scratch. All right, so again, hopefully you've taken a look at the note template and looked through the section. We're looking at example 3 now, applying our margin of error formula. It says, in a study of 250 people taking a new medication to treat anxiety, 45 reported having fatigue as a side effect. Right? If we use 45 out of 250, or that's 0.18, as our point estimate, determine the margin of error at the 90% confidence level. All right, well, from the previous page, our formula for the margin of error is this z sub alpha over 2, or critical z value, times our standard deviation of our sample proportion, which we have to use p hat instead of p because we would not know what the real population proportion is here. All right, so here's my formula for the margin of error. The textbook kind of gives that. I think it's a little note in our textbook, but most textbooks anymore just talk about that as part of a confidence interval formula, which we'll see coming up in a little bit. Now, there's a long way and a short way to find this value here that's going to be the critical z value. I'm going to draw a picture and then erase it just to give you the general idea. So if we were going to do it the long way, here we have a 90% confidence level. So the theory behind this is we know that our sample proportion is going to be normal in distribution because 250 times 0.18 times 0.82 is definitely more than 10. So remember, as long as p, n times p times 1 minus p is greater than or equal to 10, you know that your sample proportion is normal. So if we look at our normal curve, 90% confidence interval basically says, let's look at the middle 90% of all the possible values here, which would mean we have 5% up on the right tail, 5% down on the left tail. And I want to find this z-score. Well, notice the area to the right is 0.05, so our book uses the notation z with a little 0.05 subscript. The way we could do it the long way from the table is notice that the area to the left has to be 95%, so 0.9500, and then we can look in our table 5 to find the area closest to 0.9500 and get the z-score. But I'm going to advance to that table 5, and notice down at the bottom of table 5 is a little chart showing us the confidence interval critical values, those z sub alpha over 2. And whether you're doing a confidence interval or you're just doing what we're doing here, a margin of error, the most common confidence levels are 90, 95, 98, and 99%. And for each one of those, we have that critical value here. So we had 90% confidence level. Our critical value is 1.645. So this table is nice because it lets us get that value very quickly. So going back to our example, instead of doing it the long way there, we can look at the table and say, okay, very quickly I know that this is going to be 1.645 times the square root of my sample proportion was 0.18 times 1 minus that would be 0.82 divided by the square root of our sample size, which is 250. Now I'm going to punch this all up on the calculator, and this is how I'm going to do it. I'm just going to type in 1.645. So this is the calculator steps. And then you can hit times if you want to, or you can just open up the square root sign. And inside the square root sign starts a parenthesis. We're going to do 0.18 times 0.82 divided by 250, and then just close the parenthesis to close the square root. Every once in a while, we're going to hit a button wrong on the calculator, like 1 out of 5 times or something like that. You might hit a wrong button, but in general, we'll have this all in one step. And I like to show all the digits I'm seeing, or at least a bunch of them. And what you should see is something like this, 0.03997, but it goes on and on. It's possible we'll be asked to round off, so pay attention to the directions if it talks about rounding. If it doesn't say anything about rounding, you're always safe showing me all the decimal digits. What people oftentimes do is if values are provided to the nearest hundredth, like here we had a sample proportion that was given to the nearest hundredth, then what people oftentimes do is either round their final answer to the same number of decimal digits or one more than that. So it would be pretty common to see this as 0.04 as the margin of error. But either way, show all the digits and I'm perfectly fine with that. So we've calculated a margin of error, and if we apply the same idea that I mentioned back here with the margin of error creating what we call a confidence interval, we could avoid the textbook's confidence interval notation here and say, if we were asked to construct and it would be a 90% confidence interval, because we said we were doing this at the 90% confidence level, what we would do is we would take our sample proportion, which was 0.18, and let's subtract one margin of error. And again, I'm going to round this off to 0.04, so that would give me 0.14. I could take that and add one margin of error. That would give me 0.22. So I would create what's called a confidence interval that would go from 0.14 to 0.22. So what we're going to talk about next is how to apply the textbook's formula to derive this confidence interval. You know, we got to talk a little bit about what a confidence level actually means. And then we got to talk about interpreting this confidence interval. So before we get into the full examples, let's see in this particular case, this was talking about percentage of people feeling a particular side effect, fatigue. So if we're saying that our estimate for the sample proportion is between 0.14 and 0.22, and we did it at 90% confidence, where we're going with this is we want to be able to write up an interpretation that says, with 90% confidence, the true, and it would be unknown, you would not know this actual true parameter, the true unknown population proportion of patients experiencing the fatigue as a side effect is between 0.14 and 0.22. All right, so when we make these confidence intervals, when they tell us to do it at a 90% confidence level, the confidence level refers to the success rate of the method that you use. By using that z-score we did of 1.645 and using that formula, what we're doing is we're setting up an interval where 90% of all the different samples I could have collected will provide an interval that contains the real population mean that we don't know. And 10% of the different samples would create confidence intervals that miss it. So why don't you always use maybe a 99.9% confidence level? Well, the idea is the higher the confidence level, the bigger the margin of error you need, so the farther left than right you have to go. So if we want to do a 99% confidence interval, instead of having our left endpoint at 0.14, it may have had to go all the way down to say 0.09. And instead of ending at 0.22, maybe it had to go all the way up to 0.27. So to have a higher level of confidence, you need a longer confidence interval. So it's kind of like a trade-off. All right, so if we skip ahead to the next example, and in your template sheet, you just leapfrogged over the formula that's in the book for creating a confidence interval for a population proportion. We're going to do one of these population proportion problems from scratch. Now, before we get into this, one little note is I've purposely picked values here where if we convert into decimals, it's a little bit ugly, it's a little bit problematic. So I'll kind of leave it up to you. I'll show you how to enter everything in exact form, and then that way you would get what matches up with any textbook automatically. If you ever use rounded off decimals early on in a process, it's possible to start deviating by enough to make your answers at the end significantly different from what a textbook or some other source has. So let's see what we would get in this case. We have a national survey of 1,400 Americans. 775 of them said their financial standing is worse off now than it was 5 years ago. And we want to construct and interpret the 95% confidence interval for the true unknown proportion of all Americans who believe their standing is worse now than 5 years ago. Okay, so I'm going to kind of let you guys have a free pass on verifying that the distribution of the sample proportion is normal, unless the problem specifically says you have to. So again, if the problem said, to verify that you have a normal sample distribution, what you're doing is taking n times p times 1 minus p and making sure that's greater than or equal to 10. Here you have to use p hat in the place of p, so you would be taking 1,400 for n. The sample proportion is 775 out of 1,400. And then 1 minus that, I guess, would be 625 out of 1,400. And you could multiply that out on a calculator and verify that that's 10 or more. Again, unless the problem specifically says you have to verify it's normal, you don't have to do that for me. Okay, so let's copy down the confidence interval formula, because if you are doing a problem for me, I want to see this, because then I can give you points for applying the right process. Even if you have nothing right beyond this, I'll give you a chunk of points. So all I'm doing is copying down the confidence interval formula that's provided in our book. And now I gotta try to fit the pieces in. Okay, so like I said, with exact values, we can set this up with exact values if we want to, where p hat is the sample proportion, 775 over 1,400, plus and minus. If it's 95% confidence interval, that means I got to use a 95% confidence level. So I go to table 5. (95) is 1.96. And then in this square root, I can use 775 over 1,400 for the p hat. Well, 1,400 minus 775 would be 625. And then divide that by the sample size n. That would get a little bit problematic for some people to punch into the calculator. So again, if you use rounded off values too early, you're going to run into problems. But everywhere that you see this 775 over 1,400, if we want to write a whole bunch of decimal places for that, that would be 0.55357. If I were you, if they came out ugly, I'd show at least 5 or 6 decimal digits. That way, it would be more likely that I'd match what a textbook has. Sometimes it's tough if you've used rounded values, then you get answers that are a little bit different than the book, and it's hard to go back and verify whether it's because of rounding or because you did something wrong. So if you use these 775 over 1,400 and work it out, you'll get the exact values. If you want to, use the decimal instead, show a bunch of decimal places. All right, so we're going to do this out, showing a bunch of decimal places here. 0.55357, plus and minus. Now what I'm going to do is take this whole expression over here, take that margin of error, and punch that into the calculator. Then miss a parenthesis, so go back. Sometimes it takes a little bit. All right, I'm getting 0.01329. Again, it goes on and on, but basically if I showed 5 decimal digits over there, I'll show 5 over here. Sometimes we might be doing one of these problems where it says, round your final answers to the nearest 2 decimal places. you don't really want to round this guy off up here to 2 decimal places. In that case, you would still show a bunch of digits there. Here's where you might round off. So let's suppose we want to use 3 decimal digits. Then if I use the minus sign is going to give me the left endpoint. So punch this up for me, just make sure my mental math is working here. If we do 0.553 minus 0.013, that would be 0.540. And then if we do the addition, 0.567. And notice this is where, rounding can matter. Because if you take the whole thing, 0.55357, and add and subtract that, you might get one answer. Notice what would happen if somebody said, well, I need to round off to 3 digits, so I'll make this one over here 0.554 plus and minus, and make this one 0.013. Then, if you round these off, then we would actually end up with a left endpoint of 0.541 instead of 0.540, right? So again, you're always kind of better not rounding until the end. So 0.540, if you take this number, subtract this number. Now if we do the addition, looks like it's going to be 0.5667, so 0.567 if we round that off. So that would be, if we were going to round it off to 3 decimal places, that would be my confidence interval for the unknown population proportion here. One of the things that we can't afford to do is fail to interpret. Most of the time when we're asked to do a confidence interval, it's going to come with an interpretation as well. So this was supposed to be estimating the percentage of Americans who think their financial standing is worse now than 5 years ago. It was done at the 95% confidence level. So all of our proportion interpretations of a confidence interval is going to start with a statement of the confidence level. So with 95% confidence, and then we're going to say what the actual population proportion would be in this particular case. So with 95% confidence, the population proportion. Some people, like last time I wrote the true unknown population proportion, that's just kind of more specific, but as long as you have the population proportion of Americans who feel their financial standing is worse now than 5 years ago. And then say what our interval was. We're saying that it is between 0.540 and 0.567. You'll notice sometimes I put the 0 in front of the decimal, other times I don't. I don't mind whether you do or don't. But anyway, that would be an interpretation of a confidence interval. State the confidence level, then clearly specify what the proportion of interest is in this problem, and then give the values. Okay, so this section also talks about how to figure out how big of a sample you need if you want to be able to estimate a population proportion within a certain margin of error. So suppose I'm doing a study and I want to estimate the proportion of SUNY Broome students who work at least 25 hours per week, and I want to estimate it to within 5 percentage points at the 98% confidence level. How large of a sample is needed if, and there's 2 different scenarios here, because if you looked at the note packet already, there's 2 different possible formulas that you use for this. So in situation A, we're doing this under the context that I'm using the 2009 previous estimate of 38%. So if we denote p hat here to be our prior estimate, then we use the formula that our sample size n is going to be p hat times 1 minus p hat times the critical z divided by our desired margin of error and square that last part. Basically what we're doing is sort of working backwards from or solving the margin of error formula. So here's the formula that we need to do if we're going to have a previous estimate. But one thing you got to remember is always round these up. So I'm not sure what this is going to come out to, but let's say it comes out to 371.2. Doesn't matter what the point is. 371 point anything, rounded up to 372. The idea there is you can only survey whole people or whole objects at the same time. So no decimals, always round it up. So in this case, all right, so I'm going to use my previous estimate of 0.38 times 1 minus 0.38, which would be 0.62, times, all right, well, what's the critical z for 98% confidence? We're going to look up on the table here. 98% confidence, that's 2.33. And as usual, you want to enter, if it's 5 percentage points, that's 5%. But we want to use the decimal equivalent of that, 0.05. Right now we punch that up on the calculator, and when you do this on the calculator, it's going to be 0.38 times 0.62, and then times, or without the times, you can still just start a parenthesis, 2.33 divided by 0.05. But you're going to square the parenthesis there. So if I punch that up, I'm getting n equals 511.6 dot dot dot. But again, it doesn't even matter that that was a 6. That could be a 0.1 or whatever. That means that we have to bump it up to 512. It has to be at least 512 people here have to be surveyed, which is problematic. Usually you want less than 5% of your population. 512 SUNY Broome students would be more than 5% of our population. But, oh well, we get 512 as our result. Now, if we don't have a previous estimate to use, what we do is use 0.5 as a value, because that'll maximize the p times 1 minus p. If you don't have a previous estimate to use, we're going to need a little bit more than 512. The formula that we use for this, when we have no prior estimate, is the sample size. We're going to go with 0.25, because that's what we would get if we used 0.5 for p hat. And then the z sub alpha over 2 over the specified margin of error squared. So this one's a little bit easier to punch up into the calculator, because it would be 0.25 times our 2.33 over 0.05 squared. All right, I'm just going to automatically round this up, so check me on this on your calculator, but I'm getting that we would need 543 or more, so at least 543. All right, so see how the homework problems go. Try working through them. And hopefully, the more you do them, the more you get comfortable with all the different types of problems and formulas. So good luck working on them. Let me know if you have any trouble.